My dissertation is on position manipulation techniques for facial animation. The overall goal is to create visually plausible facial deformations through easy, fast, and stable interaction methods. Our methods work under a sketching interface or a classic pin and drag interface or just a strong punch to the face for soft surface deformation. These are the screen capture of my methods, just to give you an overview of what this dissertation is about. The content of this presentation is designed as first introduction, second direct manipulation of blend shapes using a sketch-based interface, third transposition-based blend shape direct manipulation, fourth is localized Burnett integration framework for facial models. Finally, I will give you a conclusion. Computer-generated characters have become ubiquitous in movies, cartoons, advertisements, and computer games. Facial animation plays a critical role for the digital character to carry emotions and personality. However, animating the 3D face is a challenging task. Firstly, face has a complex and singular surface geometry. It can be a polygonal surface, or a nerve surface, or a subdivision surface. After face requires dozens of different parameterization techniques with hundreds of parameters and thousands of different combinations. The parameterization techniques can be based on muscles, joints, blend shapes, and etc. Still, the traditional old-school methods dominate the facial animation creation. Because the adaptation of the new techniques to the existing animation workflows requires a long time. Therefore, the evolution of animation tools and workflows is slow. As a result, facial animation is a time-consuming and labor-intensive process. Thereby, our overall research question is, can we design practical tools and methods that provide plausible model deformation for facial animation? To answer that question, we have to understand facial animation process. The general facial animation pipeline is divided into three major stages. First stage is modeling, where the model is created by a scan of an actor's face or an artist's sculpt work. Then it comes the rigging stage, where the model is decorated with the control structures that are used to deform or pose the face. And the final stage is animation, where animators parameterize the rig structures to create the keyframe animation. This dissertation targets the animation stage with three different methods for facial animation. First is direct manipulation of blend shapes using a sketch-based interface. Second is transposition-based blend shape direct manipulation. The last is localized Burnett integration framework for facial models. The idea of sketching blend shapes came from Professor Veronica and J.P. Lewis. The main objective is to combine Miranda's Sketch Express with the blend shape direct manipulation framework. According to my general method overview, I attacked the framework from the sketching. Although I studied tremendous amounts of references, the closest ones are from Chang, Low, and Sconfund. But the major references are from Miranda's Sketch Express from 2011, where he offers the sketching to manipulate the joint-based model on an external drawing region. And in 2012, he improved his work to sketch directly on the 3D model. Sketching starts with a pastel-style hand drawing that is applied in 2D screen space. 2D screen space is a dynamically created virtual canvas that is orthogonal to the viewer. Stroke is defined as the ordered set of points. These points are shooted from the cursor to the screen. After applying the stroke, it's projected from the canvas onto the closest visible surface of the 3D model, and the NURBS curve is generated on the mesh. Curve is critical, and at this stage it determines the positions of the manipulators. It was selected as a cubic spline to allow the curve to lay on the surface of the model as close as possible, and it includes just enough content for efficiency. After creating the curve on the model, now it's time for twin creation. Up to now, we have one curve with 3 nodes and the model. Therefore, we have to create a physical connection between the curve and the model. I developed an algorithm to intersect the nodes with the closest points of the 3D model, and this algorithm employs a MyEmbeddedOf3 method. According to the algorithm, immediately after the curve created, it searches to equate the nodes of the curve to the closest points of the model, and each intersection position, one pin is created. After curving and pinning, we can explore how we create the deformations. Blend shape models produce the facial expressions as a linear weighted sum of target faces, and most of the professional tools provide blend shape model with their own slider interface, where each slider corresponds to each blend shape target. However, creating keyframe poses with slider interface is a time-consuming process. Direct manipulation methods address this problem by offering a mathematical framework that provides a pin and drag operation directly on the model. Direct manipulation metaphor was first mentioned by Joshi and Zhang, and after pin and drag operations were used by Tena, Seo, and Angio's works. But first time it was formulated by Lewis and Angio in 2010, they solved the inverse problem of determining the blend shape weights for specific point movements with a regularizer suitable for interactive editing. According to the algebraic perspective, blend shape model is a simple vector sum as shown in this equation. F is the final phase with all vertex coordinates, W is the weight vector, B is the blend shape matrix. However, we have to add the neutral phase to this equation because all other expressions are the offsets of the neutral phase. And the final equation is called the delta form of blend shape equation. Actually, this delta form seems like this matrix equation and used by all professional animation tools. Now the question is, how can we create a mathematical model for direct manipulation? In vertex space, the final phase is equal to dw plus f0. After adding some pins and move them, similar to this figure, the same resultant phase also equals to m plus f0. This implies there is an obvious relation between m and bw. To find the weight equation, we have to minimize the residual with a regularizer, where overline b is corresponding rows of blend shape matrix and alpha is the regularization term, such a small number, 0.0001. If we denote the minimization term as E, we have to derive its gradients over W and set it to 0, similar to this operation. And we get our final weight equation. Let's see our early results with just sketch pins and direct manipulation together. In this early form, sketching is applied just to locate the pins, and the drag operation solves the underlying weight equation. However, mathematical framework of blend shape direct manipulation is known with its instability. That means editing a certain part of the phase model causes minor changes on the other parts of the phase. If the drag is performed with slight movements, this side effect is not that obvious. However, if the artists prefer to work with gross hand gestures, the resultant pose can be unexpected. For example, it is possible to see marked movements when we try to edit eyebrows or vice versa. The solution to this problem is hidden in the weight equation. To solve that problem, I turned back to the roots, and this star report directed me to Newman's work, and Newman's work directed me to the heat method. Killing-Crane's heat method solves Varadhan's formula to compute the geodesic distance from point x to point y in a given time interval. It's a three-step algorithm. First step is to integrate the heat flow for some fixed time. Second step is to evaluate the vector field. And the final step is to solve the resultant Poisson equation. Heat method is an elegant method to create geodesic circles for confining the weights to the local geometry of the phase. It has two main advantages. First, it can be applicable to any surface type from point clouds to polygon meshes. Second, it works with sparse linear systems that can be prefactored once and later solved many times with a notable speed. In our models, heat method speed is around 0.02 seconds. Now, how I can confine the weights by using the heat method? I would like you to focus only one single pin in the job area. Each time when I create a pin on the model, I update my blend shape matrix. And it is the most important input that I cannot control manually in my weight equation. The content of the blend shape matrix consists of the deformation components from each blend shape target. Some have little effects such as W1 and W2. Some have tremendous effect on the pinned regions such as W3 and W9. During our analysis of those targets, we noticed that the source of the instability is the small components for this particular case. For example, for a pin in the job, small components may belong to eyebrow or eye itself, so they are useless for job deformation. I create the geodesic circles with a user-defined minimum and maximum radius to find the actual circle as a certain limiter. And for each pin, these circles are created by keeping them in the center. And I iterate all the norms of each target deformation component with this conditional operation. Visually, that conditional operation implies that if the norm of the deformation component is not enough to pass the boundaries of the actual circle, then eliminate it, because it belongs to the other parts of the face. If it passes the boundaries of the actual circle, it definitely belongs to the pink region and keep it in the blend shape matrix. The video shows that minor localization approach is a solid way to stabilize the direct manipulation. Wherever we apply the sketching and pinning, it only deforms the desired region. This doesn't require any pre-processing, and it gives stable end results. Furthermore, there is still one more element that I can use to create deformation. That element is the curve itself already positioned on the model. But the question is, how can we add the curve to the deformation process? At this stage, I would like to introduce the horizontal curves. Horizontal curves approach has been employed by transportation engineers for many years to curve the highways. And surprisingly, it can be useful in our method. Because it nicely fits to mimic the pin drag just by using the curved entities. It can also be considered as a banded wire which has the pins in both ends and in the middle. In the curve domain, the drag displacements mostly depend on the curve angle, which is already fixed as 3 radians by the cubic spline and the radius of the curve. Therefore, we have enough parameter to calculate the displacement by using trigonometric principles as shown in the figure. Calculation seems straightforward, but the results are efficient and promising as illustrated in the image. The direction of the deformation is dependent to the normal direction of the middle point in y-axis. If it's negative, that means curvature is downside and the deformation is upwards. If it's positive, that means the curvature is upside and deformation is downwards. In our method, every step complements each other. For example, if I apply sketching without localization, the results will be unintuitive as shown in the figure. However, if I apply sketching with localization support, the results are in the direction of the expectations. When we compare the sliding interfaces, if there is no localization, we can easily see that the weight function parameterizes almost all the blend shape targets. On the other hand, in the localized case, just the relevant weights are parameterized. In the symbol chart, x-axis represents each blend shape target and y-axis shows the values of these blend shape targets. Localized red lines show how the intuitive results should look like. And with all these non-zero parameters, non-localized blue line completely breaks the meaningful expression that the animator is trying to create. This simple chart proves that our localized direct manipulation produces more clear and stable facial poses under the sketch-based interface. In this video, we can see the results. When the user applies the sketch, immediately he gets an approximated deformation, and then he can fine-tune the model to obtain the final pose. Our method is easy to use and reduces the consumed time to create blend shape keyframe poses. And also, it is possible to apply our method to other blend shape models. As a summary, our method allows to create meaningful localized blend shape facial deformations, and it provides a precise connection between sketching and manipulators, but most importantly, it allows to manipulate multiple blend shape targets at the same time with just single hand drawing. After my solution on localization, Professor Veronica and JP Lewis offered me to study the Jacobian transposers, and a new research line opened. Our new chapter is about transposition-based blend shape direct manipulation. From the algebraic perspective, I already mentioned there exists a pseudo-inverse relation between the blend shape mathematical model and the moved points. Inspired from Jacobian transpose method from inverse kinematics, is it possible to obtain a more stable weight update by using this formula? For that purpose, I studied these references to seek that relation. The explicit definition of pseudo-inverse can be written in the upper right-hand form, but in some particular cases, B may not provide a full rank, and thereby B transpose B element of the equation turns into a singular state. As we saw before, Lewis and Angio's weight function solves this problem with Tukanov regularization term, and we know this formula very well. However, it's a pseudo-inverse, and pseudo-inverse is very well known with its instability. But now, we turn back to the purest form of pseudo-inverse to see why it is not stable. The major reason can be explained as pseudo-inverses tend to apply many non-zero values in its columns due to the spreading effect of matrix multiplication. And in inverse kinematics, there exists the same relation between IK handle and the target point. However, in 1993, Wellman addressed this instability of pseudo-inverses and offered the stable Jacobian transpose method. And if I apply the same principle to update the blend shape rates, my matrix equation shrinks into this form. And intuitively, this form is the direct projection of the pin moments onto the blend shape matrix, and it makes a perfect sense. To test our new method, we created a test pose with the weight values shown in A, and tried to get the same pose with our transposition method in B, classic pseudo-inverse method in C, and Leb's and Angio's method in D. It is clear that we could get the closest result to the actual values only with our transposition method with negligible error values. D gives better results than C, but C completely fails. In another case, we tried to catch the same poses with the same methods, but the error produced by B and C makes it almost impossible to get the desired equal poses. Besides in B and C, pin movements start to move away from the model. After I pushed the limits and I did the most precise comparison by applying all the values that we obtained from the previous test on the root mean square deviation. Results obtained from our transposition method outperforms the other two approaches, and the results from the transpose method are almost not observable on the model. Video shows the side-by-side comparison of all three methods. I believe there is no need for further explanation because our method's intuitive results and stability is very obvious. As a summary, our transposition method provides an alternative mathematical solution to the direct manipulations. It is stable and eliminates the unexpected deformations during the artistic editing. Our new chapter is about soft surface simulation with physics. Worded integration first used in a computer game called Hitman 47 to simulate soft surface interactions. Physics solvers for surface deformations have been very popular due to their realistic results. However, existing solvers and the frameworks deform the model as a whole. Despite the advances in technology with significant computation power, simulating the complex theories is still very expensive. But is it possible that reducing the deformation influence region increases the performance and efficiency of the physics solvers for the same visual deformation, without any parallelization, without any supercomputer? The major reference for the worded integration on computer animation are from Jacobson, Müller, and Stem. Classical approaches for simulating dynamics are based on mass spring networks, and the equations of motion solve the velocity, acceleration, rotation, position, etc. Also, physics is based on the definition of the applied forces. Majorly, Euler method dominates the time integration scheme. Euler is a first-order differential equation representation and not a stable approach because it is known with its overshooting problem. As an alternative to the classical physics approaches, worded integration-based methods offer to replace the mass spring networks with hard names. Worded integration is a refined numerical integration method to define the equations of motion, and it's the central difference approximation to the second-order differential equation. According to worded representation, the position updates are defined as this equation. In this form, velocities are stored implicitly and there is no need to calculate them explicitly. In our framework, we modified the worded representation with a damping parameter to obtain stability and overall aesthetics. In this type of dynamic system, the position corrections of the interconnected components are computed with the idea of projected constraints. From left to right, image shows the projected constraints for stretching, shearing, and bending. The displacements of each point calculated with a constraint function in this form, where Q is the vertex positions and delta Q is the corrected displacements. This constraint function is solved by employing the first order Taylor expansion. And the corrections become like the above equation with point masses and Lagrange multiplier. And these two equations are the base for position updates in each simulation step. We employ three different position constraints. First, the vertex-based stretching with a length function. Second is the edge-based shearing with an angle difference function. Third is the face-based bending with a face angle difference function. All updates are performed in a nonlinear Gauss-Seidel fashion. That means first compute, then get the results and update, and repeat this process till the end. We present our soft surface results under the collision constraint, which is also computed within the computation rule. It is unilateral, straightforward, and effective in terms of rapid results. The dynamic solver that I have till now is very robust and stable, but very slow. For a face model with thousands of vertices, edges, and faces, just one simulation step takes around 20 to 30 seconds. So I have to do something. And I remember the heat method again. The heat method comes into the game, but this time not confining the weights. In this particular case, heat method is employed to precompute the desired deformation influence area. And reducing the deformation area from the whole model to an arbitrary region immediately increases the performance for simulation step. As I mentioned, for the whole model, each simulation step is 20 to 30 seconds, but this timing reduces to 1 second or less for 3 unit range area and gives this exact same deformation. Heat method performance is another factor for the overall framework performance. The image shows 1 unit range precomputed soft area in A, 6 unit range precomputed soft area in B, and 12 unit range precomputed soft area in C. For a large area like 12 unit range, the timing is around 0.2 to 0.25 seconds. For a small area like 3 unit range, it is less than 0.05 seconds. After performance, we check the visual quality of the surface deformation after collision under different projected constraints. A is only constrained with stretching, B is constrained with stretching and shearing coupled, C is constrained with stretching, shearing, and bending altogether. The video presents our results. The blue colored region is computed with the heat method immediately after touching to the model for 3 unit range, and only that region has the soft surface properties. The rest of the model conserves its rigid behavior. The performance is dependent to the region size. It is much faster in range 3, little slower in range 6, and for the whole model we had to wait a little bit. Processing continues. The visual quality is dependent to the projected constraints. Left is just stretching constraint, middle stretching and shearing together, and right is stretching, shearing, and bending all together. And we believe this quality fits for cartoon characters or background characters in animation movies. Damping is also another factor for overall cosmetics. Our framework uses stable worlet integration with position-based geometric constraints. Nicely combines the heat method with a physics solver and provides a notable performance for physics-based facial deformations. In this dissertation, we propose 3 methods which allow to produce plausible, robust, and stable facial deformations. The main contributions are listed as: first is the blend shape manipulator placing algorithm, second is the facial sketch-based control method, third is the localized blend shape direct manipulation, fourth is the transposition-based direct manipulation, fifth is the localized physics solver for facial models. All 3 methods are implemented on 3 different frameworks. Although the foundations of the methods differ, frameworks share the same goal. They are simple, fast, intuitive, stable, easy to use. They can work on any face model. They are easy to integrate to current animation workflows, since all implemented under a professional tool as its plugin. At the beginning, I asked a question. Can we design practical tools and methods that provide plausible model deformation for facial